Okay, let's look for our intervals of increase and decrease along with our local extrema. So remember what you're going to need to do. You're going to need to find your critical points, for starters. In order to get your critical numbers, you're going to need to find the first derivative of the function. So you're going to have to carefully differentiate f of x. Now, what was f of x? F of x is given by the function x to the 1/3 times 4 plus x. There's a couple of different ways to go about this. You can just do the product rule right now, right? You've got a product of two factors, x to the 1/3 and 4 plus x, or you can multiply the x to the 1/3 into the brackets and then expand it into two terms and then do the power rule on each. But no matter which process you choose, no matter which approach you use, you're going to need to simplify. You're going to have negative exponents no matter what. You're going to need to turn those negative exponents into positive exponents by moving the powers of x down to the denominator. Once you do that, you're going to want to get everything combined into one fraction by getting a common denominator. Once you do that, what you're going to end up getting, so as you can tell from what I've just described, there's a non-trivial amount of work involved, but what you're going to end up getting is you'll get f prime of x is equal to 4 plus 4x over 3x to the 2/3. That's what you'll end up getting. Okay, so if you'd like to see some of the details behind that, if you get stuck trying to work that out on your own, or you get something different, check the complete version of the course notes in section 4.4. One of the examples is exactly what we're working through, so check that section and you can see exactly where this comes from. But you should try to do it on your own at this point. This is something that you should practice working through on your own. But this is what you get when you fully simplify f prime of x. Okay, so now we can find our critical numbers. Let's start by finding our type 1 critical numbers. Determine when f prime of x is equal to 0. Well, when's that going to happen? That's going to happen when the numerator of this fraction is 0. And we can do this and we can immediately make that conclusion because we've completely simplified the derivative into this fraction. So by doing that, this makes this next step go a lot more smoothly. Because if all you did was take the derivative in one step and use the product rule or whatever approach you did, and you had a bunch of terms with negative exponents, it would not be that easy to identify when this is going to happen. But because we've written it as a fraction, we can say that f prime of x is equal to 0 when 4 plus 4x is equal to 0. And you can solve that for x. You're going to get the solution x is equal to -1. Just bring the 4 over to the other side, divide everything by 4, and you'll get x is equal to -1 as your solution. So that's a type 1 critical number. The type 2 critical numbers, we need to ask the question, when is f prime of x undefined? Well, that's going to happen when the denominator of the fraction is equal to 0. So we can say when 3x to the 2/3 is equal to 0. And, well, how do you solve that equation? Well, first divide both sides by 3, and you're just going to get x to the 2/3 is equal to 0. And again, it's a positive power of x. It's going to be equal to 0 exactly when x is equal to 0. So that'll give you the solution x equals 0. So those are our two critical numbers. I'll just draw a box around them so we can see them easily. And then next, what we're going to do is we're going to set up our first derivative table. So I'll do that up here. It looks like I got room to squeeze it in. So we're going to need 4 rows. 1 row for the numerator, 1 row for the denominator, and then 1 row for f prime, and then 1 row for f. Okay, and then we're going to need to do 2 slices down, 1 for each critical number. So we've got -1 and then 0. And then we'll just pick a sample point in each one of those regions. So how about -2, -1/2, and then +1? How about that? Those will work fine. So plug those in. Plug -2 into 4 plus 4x. Well, if you plug it into x, you're going to get 4 plus 4 times -2. That's going to be 4 minus 8, which is going to be negative. If you plug -2 into 3x to the 2/3, if that looks intimidating, think about it this way. No, I'm just going to put a plus here. And here's why. In fact, I'm going to put a plus here and a plus here without even looking at those 2 points. Here's why. Okay, 3x to the 2/3 is actually, what is that as a radical? That's going to be 3 times the cube root of x squared. So no matter what you plug in for x, you're going to square it. And this part inside the cube root is going to be positive. So you have the cube root of a positive number, which is going to be positive, multiplied by 3, which is also positive. Okay, so watch out for little things like that. You can save yourself some time if you make those observations. We don't even have to plug numbers in. This is, by default, this is always going to be a positive number, except when it's 0, but that's going to happen at -1. Or pardon me, that's going to happen at x equals 0. So we're never going to plug in that point because that's actually the critical number. So for that reason, because of the way we broke this down, it's going to be positive all the way across. You don't even have to plug in values. Okay, well, for the first column, you've got a negative. It's not a product because it's a fraction, right? But it's the same as if you had a product. You've got the numerator is negative, the denominator is positive. A negative divided by a positive is going to be negative. So your function is decreasing on that interval. And then if you plug in -1/2 for x, 4 times -1/2 is actually -2. So you're going to have 4 minus 2, which is positive. So 2 positives make a positive for f prime, and then that means your function is increasing. And then lastly, if you plug in x equals 1 to 4 plus 4x, you're going to get 4 plus 4, which is positive. 2 positives, again, will make a positive, so the function is increasing on that interval as well. So that is your first derivative table. Do you have any local mins or maxes? There's no local max, but there is a local min that occurs at -1. So let's figure out what the y value is of that point now. So f of -1, remember you're plugging this into the original function. So we're going to have -1 to the 1/3 multiplied by 4 plus x. And our x is -1 in this case, so we're going to have 4 plus -1. So this is plugging -1 into the actual original function. Right? That's this function here, plugging in -1 to this function. Okay, well, what do you get? This is -1 to the 1/3. That's the cube root of -1. Cube root of -1 is -1. And 4 minus 1, which is really what you have in here, is +3. So you've got -1 times +3. The result is going to be -3. So that's how you can get the y-coordinate of that local minimum. So let's summarize everything we have now. So f is decreasing on the interval -∞ to -1. And f is increasing on, well, there's 2 intervals on which it's increasing. -1 to 0, as well as 0 to infinity. Right, you can get that from the table. It's decreasing from -∞ to -1. Then it's increasing from -1 to 0, as well as 0 to infinity. Stated as 2 separate intervals. Just stay in the habit of doing that. Don't try to be clever here and combine this all into one interval. Sometimes you can do that. Sometimes you'll be correct, and if you do it in general, sometimes you'll be wrong, and it's just a road you don't want to go down. And just stay in the habit of just specifying each of these individuals as separate individuals connected with the union sign. That's how you should write this for now. And then we've got our local minimum. Let's put it in over here. F of -1 is equal to -3 is a local minimum. Okay, so that is our summary for part D. So now we'll move on to part E, the intervals of concavity. So that's what we want to find now. We want to find out where is our function concave up and where is our function concave down. So that was part E. So, well, to find the intervals of concavity, we're going to need to investigate our second derivative. So what will you get if you work out the second derivative? And then carefully simplify it. You'll end up getting the following. And again, the details are in the notes for anyone who still needs a bit of assistance working through this. No problem. Try it on your own though, because you want to get confident and be able to do this independently. But if you're watching this video and you're not really sure how I get this, the answer that I'm writing down now, it's going to be 4 times x minus 2 all over 9 times x to the 5/3. If you're not comfortable getting this, try it on your own, but if you get something different or you're having trouble simplifying what you get into this fraction, then no problem, just look up the section 4.4, the complete version of the notes for that section, and one of the, like I said, one of the examples has this worked out in detail as well, and it has all those extra details, even the details that I'm omitting at this stage. Okay, so that's what you'll get for your second derivative. So, and again, I'm just going to emphasize, don't take my word for it. Check this. That's an exercise for you, that you should do. If you want to watch the rest of this first, go ahead, but at some point go back and check the details to make sure that this is correct. Okay, so we're going to look for some special values here. We want to find where is f double prime of x equal to 0 and where is it undefined. So f double prime of x is equal to 0. That's going to happen when your numerator is equal to 0. So what's the numerator? 4 times x minus 2. Well, the 4 is never going to be 0 because it's 4. It's not a variable. It's just a constant and it's non-zero. So it's really just where x minus 2 is equal to 0. And that's going to happen when x is equal to 2. Okay, so that's one important value for our second derivative table. Now, when is f double prime of x going to be undefined? It's going to be undefined when the denominator is equal to 0. Well, 9 is never 0. So the only way the denominator is going to be 0 is if x to the 5/3 is equal to 0. And again, x to the 5/3 is a positive power of x. So a positive power of x is going to be 0 exactly when x is equal to 0. So that's how we're going to get our other value. Okay, so that is the two values that you're going to use on your second derivative table. So let's draw our second derivative table here. So again, we'll have 4 rows, 1 row for the x minus 2. Notice I'm skipping the 4, really, because multiplication by positive 4 is not going to have any effect on the sign, so I can drop the 4 if I want. And then for the 9x to the 5/3, I'm just going to write x to the 5/3. Then, because multiplication by positive 9 does not affect the result. Then, what about the quotient? If I divide these two, I get something that has the same sign as f double prime of x. And then our last row is going to be devoted to f of x. Okay, then we'll have 2 slices, one for each of our important values that we just found to the left, so 0 and 2. And then we're ready to fill in this table. So pick some sample values. How about -1, +1, and 3? So if we plug -1 in for x minus 2, we're going to get a negative value. If you plug -1 into x to the 5/3, well, let's check that. That's worth checking carefully. What do you get if you go -1 to the 5/3? Well, by definition, that's the cube root of -1 to the power of 5. So you have the cube root of, what's the inside? -1 to the 5, that's an odd power of -1. So an odd power of -1 is just going to be -1. So -1 to the 5 is just -1. But now you have the cube root of -1, which is, again, -1. Okay, so that's how you can check these in detail. Don't put pressure on yourself to do them in your head. You don't have to do that. You can always just work it out carefully using properties of exponents and numbers and whatever the case may be. It depends what this is, what properties you use, right? But if you handle it carefully, I won't throw anything at you that's unreasonable, ever. Okay? Okay, so the negative divided by a negative is going to give us a positive. Then that means our function is concave up to the left of 0 on the number line. Now, what do when we plug in 1? Plug in +1 to x minus 2. You're going to get 1 minus 2, which is negative. If you plug 1 into x to the 5/3, you can check in the exact same way that I did this, but you're going to end up getting +1, which is positive. So don't be afraid to actually do the work, right? Don't be hesitant. Take that one and just work it out carefully. Really, it comes down to understanding what that 5/3 really means. And if you just unwind it, one step at a time, you get your answer. But you'll get +1 if you plug 1 in here. Okay, so you have a negative divided by a positive, which is negative. So function's concave down there. All right, now plug in 3. For our last column, you're going to get positive for both. Okay, I'll leave it to you to check that in detail. So a positive divided by a positive is a positive. Therefore, the function is concave up there. All right, so that is all of our information. So let's finish it off. F, and by finish it off, I mean summarize it. So F is concave up on 2 intervals from negative infinity to 0, unioned with 2 to infinity. And where is F concave down? In between, right? F is concave down on the interval 0 to 2. So that gives us our intervals of concavity, so that is the end of that step. Now for part F, and you might like to combine steps E and F, there's nothing that stops you from just merging these into a single step. You don't have to enumerate the steps in the exact same way I did it. What matters is that you check everything. Okay, to be honest, I didn't start enumerating the steps like this until I started teaching this material. If I was solving these problems on my own, I would just make sure I check everything. I don't really always need to enumerate it, right? What matters is that you don't miss any of these things. So as long as you have the habit of checking everything, it doesn't matter what you call the steps. You can call them at 1, 2, 3, 4, 5, 6, or you can call them A, B, C, D, E, F, or you can merge them into bigger steps so you don't have as many. It doesn't matter. As long as everything gets checked, it doesn't matter what you call the steps. But just to keep things simple, I will follow the same process that I laid out at the beginning, right? I laid out these 6 steps, so we're on the last one now, finding the inflection points. But like I said, you can merge these 2 together if you want. There's nothing saying you can't do that. Okay, so let's get inflection points. You might want to look back up at your table to see if there's any concavity changes. And of course, there are. There's 2 concavity changes, one at 0 and one at 2. So that's because 0 and 2 are both in the domain of the function, we got 2 inflection points here. So let's work out what their y values are. So f of 0, for starters, plug in this value to get the y coordinate. F of 0 is equal to, remember what f was? It was f of x is x to the 1/3 times 4 plus x, and you have that available too if you have your paper out in front of you. So take a look. But f of 0 is going to work out to be 0 to the 1/3 times 4 plus 0. So 0 to the 1/3 is just 0. So you've got 0 times 4, which is 0. So that tells you what the y coordinate of one of the inflection points is. That's actually the origin, right? Which ended up being that was your intercept, the x and y intercept. But it's also an inflection point according to step F. So that will be good information to have when we go to do our sketch. Then f of 2. F of 2, we're going to have 2 to the 1/3 times 4 plus 2. So 2 to the 1/3, that's a cube root of 2. And 4 plus 2 is just going to be 6. So this is going to be 6 times a cube root of 2. So don't plug that in to your calculator at this stage. Don't round it off. We want exact values. Even though our sketch is just a hand-drawn sketch, we still want to keep all our values exact, and we're not going to make any claims that are false. So we still want to pay very careful attention to detail. Okay, so leave this as 6 times the cube root of 2. You can't simplify it any more than that, so we'll just leave it be. So let's summarize our inflection points now. So we've got one of them at the origin, right? F of 0 is equal to 0, so the origin was one of the inflection points. And the other inflection point had an x coordinate of 2, right, up here, and we plugged it into the function to get 6 times the cube root of 2 as the y coordinate. So that is your inflection points. So now we have absolutely every piece of information that we are currently equipped to find. So now we're ready to actually start the graph, which we will now do on the next page.